Hello everyone. So, today I am going to discuss about 1D optical waveguide, just to get an idea that how this optical waveguide can be designed and what is their working principle. Since we have learnt that metal plates cannot be used for waveguiding, or metal waveguides cannot be used for optical waveguide because of losses etc., and dimensional reduction. And towards that end, we will take a model called a ray optics model. Not directly we will solve Maxwell's equation to understand that how waveguide operates. Rather, we will try to understand with a very basic principle how 1D optical waveguide works, and you can realize, visualize. Fine. So, for that purpose, let us consider, to understand that, let us consider two medium 1 and medium 2. They are separated by interface with a yz plane. This is your x axis, this is your z axis, this is y axis. So, that means x axis, y axis, z axis, like that. And then the medium 1 is characterized by its permittivity epsilon 1, epsilon 0, epsilon 1 r. So, that is the relative permittivity for the medium 1, and it is considered as a non-magnetic material. So, mu r equal to say 1, and dielectric material where we can consider the conductivity tends to 0, very low. So, similarly, we consider another dielectric medium 2, where that is also sigma 2 equal to tends to 0, non-magnetic. So, again mu r 2, this is mu r 1, mu r 2 also equal to 1, and permittivity is epsilon 0, epsilon 2 r. So, that is how we can define two media, and they are meeting at yz plane. Let us consider that one normal to the yz plane is sketched at O. That can be, you can consider coordinate x, y, z, any x, y, z, that can be 0, 0, 0, something like that. This is the medium, two media 1, media 2, and I would like to understand what happens a electromagnetic wave propagating from medium 1 towards medium 2, whether we can get a certain reflection, so called total internal reflection, similar to what we could get in a metal interface, dielectric metal interface. That is what the idea we would like to understand. Okay. Now, little bit going ahead, if I try to find out the so called impedance eta value, eta 1, we know this is the definition of eta 1 for a given material characterized by epsilon 1, mu 1 and sigma 1 for a given frequency omega is like this. So, whenever I am putting this one equal to sigma 1 equal to 0, then mu 1 equal to say mu 0, because mu r equal to 1, then we can get say this one 0, j will cancel. So, it will be omega will cancel. So, you will be getting mu 0 times epsilon 1 equal to epsilon 0, epsilon 1 r. So, again you know that mu 0 by epsilon 0 is the eta naught. So, that is the constant for the free space, integrating impedance for the free space. We know the value is 377.6 ohm, something like that, free space. So, we can write this one equal to eta naught by n 1, where n 1 is nothing but square root of epsilon 1 r. So, dielectric constant, if you are just consider, as long as dielectric constant is real, the square root also will be real, we call it as a refractive index of the material of the medium 1, refractive index. So, similarly, similar fashion, this is also dielectric material medium. So, we can also find out eta 2 is nothing but eta naught by n 2. N 2 is the refractive index of the medium 2, again refractive index. Okay. So, that means if it is a dielectric media and we want to see how electromagnetic wave behaves in the interface, we only need to know N1 and N2. N1 and N2 if it is known, then we will be able to explain how electromagnetic wave behaves in the interface. Okay. So, instead of all these parameters, we have to remember only N1 and N2 if it is a dielectric medium. Okay. Now, that is what we have written eta 1. Obviously, that will be frequency dependent because refractive index is frequency dependent, because we have shown earlier that epsilon r can be frequency dependent. Okay. So, omega equal to your 2 pi c by lambda or 2 pi nu angular frequency. Nu is the linear frequency, lambda is the wavelength. Similarly, eta 2 we have written like that. Okay. Now, let us see what actually happens. You just consider a electromagnetic wave is plane wave propagating in k I direction, making an angle with the normal theta I. K I is the propagation vector, wave vector, and you can consider this is just a plane wave, parallel phase front you can sketch, so that you can consider this is your lambda in that medium. So, when plane wave comes and make an incident in the interface, so we can assume that fraction of the power or field will be reflected along k r direction. That will be also, you can consider that is also plane wave. That will be plane wave, plane phase front. You can think of it is extended infinitely, but for this understanding purpose we have limited the width. Similarly, a fraction of the electromagnetic wave power that will be transmitted to the second media, and that is also will be is going to be also plane wave. It is going like that, and that will be the lambda 2 here. This is lambda 1 here, and that will be lambda 2 here. It will be lambda 1 here, because the medium is same, lambda 1 and lambda 1, and here will be lambda 2. Okay. And one thing we should keep in mind that this k I can be written as this one. We can consider that k I is lying in the xz plane. The screen is the xz plane, in the screen itself k I. So, that is why you have x component and z component. Okay. This is not a vector sign, this should not be there. Okay. Similarly, so you can decompose into z component and x component. Similarly, the k r we can decompose into z component and x component. That is what reflected wave vector k r x, it is negative direction, negative x direction, and this one is the positive direction, k r z will be there. Okay. So, that means the difference between incident wave and reflected wave is that difference of the k r x component is reversed, that is it. And we can define k I is the wave vector. You know, wave vector earlier we have discussed, that will be omega by c, n1 omega or 2 pi by lambda n1 lambda. That is the wave vector. Depending on the medium, you have to n1, and it is a mode. So, you can ignore the direction. So, whatever value you are getting, you can say that k r also will be same, just in the same medium. So, wave vector, that means value, wave number, so called wave number will be same, because it is in the same medium, incident wave and reflected wave same medium. So, 2 pi by lambda n1. And in case of transmitted wave vector, so wave number will be k t omega by c, instead of n1 we are writing n2. So, that can be omega equal to, again same way we can write 2 pi c by lambda, c c cancel. So, this is the another way of representation, and k t vectorially you can express like this. All right. So, for the situation is set now. Now, we need to understand a little more. What is that? Let us think. Okay. The wave, this is k I propagating in this direction. It has x component and z component. So, we can consider the incident wave has a associated electric field can be represented like this, plane wave representation. It has a amplitude, obviously it will be a vector, we can define which direction it can be, and associated magnetic field also will be there, but since they are plane wave, so phase factor will be same for electric field and magnetic field. So, k I dot r minus omega t, this is the space dependent phase factor, this is time dependent phase factor. Likewise, if anything reflecting, so reflected amplitude I can define E 0 r, and we can write k r dot r omega t and k r omega t, same phase magnetic field and electric field, you can write phase will be same. By the way, this r is nothing but you can just consider any position vector a x plus a y plus a z. So, this is the case. Similarly, for transmitted wave also we can just say that okay, transmitted wave amplitude will be this one, that will be vector also. Phase will be, instead of k I k r, k t we have written. We have assumed that frequency does not change, it is all linear medium, no frequency is going to be changed, and associated magnetic field we can define like this. Good. So, next thing is that okay, we have considered electric field, but as we mentioned that what direction of electric field we can consider for our discussion. Okay. We have two choices, one is called so called TE and another is TM. So, this is TM, transverse electric field and transverse magnetic field. So, for transverse electric field we can consider E vector has only y component, x component is not there. So, this is corresponding to E x component, that is 0, E z component, that is also 0 I have represented, and E y component only there. So, E field I can consider that is actually oscillating along y direction, that is your E field, we can say that it is oscillating, it must be perpendicular to the k I, that is correct. And magnetic field you can assume that, you have to assume that magnetic field is also perpendicular to the k I vector, and that should be perpendicular to the E vector also. Since E is oscillating along y direction, I can say that magnetic field will have, we should be in the x z plane. So, that means I can consider magnetic field will have x component and z component, no y component. So, that means I can consider plane wave, electromagnetic wave is having electric field y component and magnetic field h x and h z, that would be sufficient for electromagnetic wave propagation along k I direction. It can carry electromagnetic energy in that direction. So, that particular type of polarization we call the transverse electric field. That means transverse means it is actually perpendicular to the screen, electric field is perpendicular to the screen, y direction. Similarly, for TM polarization we can consider that okay, magnetic field is the perpendicular to the xz plane, it is along y direction. Okay. That means, in this case electric field is the tangential component to the interface, and for TM magnetic field is the tangential component to the interface. So, magnetic field is the perpendicular to the screen, and if magnetic field is this direction, earlier case magnetic field is like this, here it was oscillating like this and electric field oscillating in the y direction, and now it is a reverse case. You can consider this one is your so called, this one will be your H field and this one will be your electric field. Electric field will be oscillating in the xz plane. So, x component, z component is there. In that case, that will be called as a TM polarization. So, in this case we will have Ex component, Ez component and Hy component. So, that means all the 6 components can have in a plane wave, but we can decompose into TE polarization and TM polarization of this kind, and we can treat them independently because they can carry energy independently. They can be a solution, independent solution. Okay. So, if some other polarization is there, obviously we can decompose into TE and TM. Next we try to see, for example, TE polarization and TM polarization if I consider and making an incident, I can find using our boundary condition how much fraction of electric field or electromagnetic wave will be reflected. So, using the boundary condition, that equation is actually that reflection coefficient gamma T can be derived, and Fresnel was first time Fresnel derived first using boundary condition. That is why we call it as a Fresnel's equation, Fresnel's equation of reflection for gamma T, and that is actually for any two media. We have discussed earlier also that if two media and they are characterized by eta 1 and eta 2, then that is actually reflection coefficient depends on our incident angle theta I, theta t and so on. And for TM polarization everything is same, only theta I and theta t they will be changed, they are interchanged. So, instead of cos theta I, here you are writing cos theta t and here you are writing cos theta I, otherwise same. So, another important thing you can notice from this equation that numerator denominator they are same, just plus minus difference both for TE polarization and TM polarization. And one more important thing, interesting point you can note that suppose theta I equal to 0, that means normal incidence, this theta I equal to 0, obviously your theta t will be equal to 0. So, in that case your gamma T will be equal to eta 2 minus eta 1 by eta 2 plus eta 1. Similarly, here also if we put theta I equal to 0, theta t also will be equal to 0, then gamma Tm also will be eta 2 minus eta 1 by eta 2 plus eta 1. So, that means for normal incidence TE polarization and TM polarization their reflection coefficient is same, but if it is a little bit angled, then reflection coefficient for TE and TM polarization is different. Okay. That is one of the application people use for various purpose, sometimes polarization filter purpose people use, just you have to choose right combination of material, dielectric 1 and dielectric 2. We are not going into that direction, instead we will move forward. Suppose it is a dielectric medium, we have learned that instead of eta we can just the medium is characterized by refractive index only. Eta 1 and eta 2 can be represented by refractive index because conductivity is 0, non-magnetic material, so on. So, if I just substitute eta 2 with this one and eta 1 with this one, then I get n1 instead of eta 2 it will be n1 cos theta I equal to n2 cos theta t, okay, and n1 cos theta I n2 cos theta t. This one you can remember, this E0 r means reflected amplitude, this one E0 r divided by E0 I, that means what is the reflected amplitude and you are normalizing with incident amplitude, that is your reflection coefficient. So, now the Fresnel equation in terms of refractive index. So, if you know the refractive index and if you know the incident angle, then you can find out what is the reflection coefficient for TE polarization and what is the reflection coefficient for TM polarization. They are different because theta I, theta t little bit different. When it is angle, their reflection coefficient is different. For dielectric non-magnetic material to material medium interface, the reflection coefficient we can easily find out. Okay. So far so good. So now let us move on. I have just written down same thing, the reflection coefficient for TE polarization, and you should keep in mind that TE polarization I am just retaining these equations, this component, so that the things you can remember easily. So, you can correlate here. So, this is gamma TE reflection coefficient gamma TM. So, theta I, theta t dependent as well as n1 n2 dependent. Okay. Now, few more thing I have just retained here, KT earlier we have discussed, we are retaining, and we can define that n2 is nothing but dielectric constant, same thing whatever we have discussed, we are just keeping here everywhere just to follow up. Some of these parameters we need for further discussion, that is why I retained here. So, all this k vector. So, I can have longitudinal component and transverse component and longitudinal component. Transverse means along x direction, longitudinal means z direction components are there for incident wave, for reflected wave, for transmitted wave. Fine. So, now one important thing you must understand that this Kij, Krz, Ktz, they are all tangential component of the wave vector, and from the boundary condition we know that they are basically same Kij, so they should be continuous Krz and Ktz, they are equal. Now, what is Kij? Kij, if you see, if it is this direction. So, if this is theta, this is 90 minus theta I. So, Kij, this component basically, this component is Ki times sin theta I. So, that is actually Kij, this one means Kij, and this one is Krz, because if you just z component means if this is theta r, this would be theta r. So, this will be 90 minus theta r. So, that will be Krz means Krz is Kr sin theta r. Similarly, Kt, so you have this is z direction, this is your x direction. So, if this one is theta t, this is theta t. So, this is 90 minus theta t. So, if it is Kt, so Kt sin theta t, that will be your, this is Krz, this is Ktz. So, longitudinal components, that means transverse in the interface, the transverse component of the wave vector, they must be continuous. That also you can prove using the boundary conditions. Any standard textbook, again electromagnetic theory textbook, you can get that one. I have just borrowed directly that thing. Fine. Next thing is, what is that? So, this one little bit modified. So, Ki, we know that Ki is this one 2 pi by lambda n 1, Kr is 2 pi by lambda n 1, Ki, Kr, they are same in the same media, and Kt, instead of Kt I am writing 2 pi by lambda n 2. Okay. So, if I just use this thing, this formula, this condition, then I get two things. If I just compare these two, 2 pi by lambda cancel, n 1 n 1 cancel, sin cancel. So, theta equal to theta, that is actually we know as law of reflection. And if we compare these two, then you see n 1 sin theta I equal to n 2 sin theta t, n 1 sin theta I equal to n 2 sin theta t. This is known as Snail's law of reflection. That is this thing, law of reflection, Snail's law of refraction, that means that relates incident angle to refracted angle, and this relate incident angle to reflected angle, that is why law of reflection. So, this one actually should be equal to this one, and this theta t and theta I related with the law of refraction, that actually we get from the Maxwell's equation also, the Snail's law. Okay. That is our school level we learned that. Now, here we are understanding how that can be extracted from the boundary condition. Good. So, next thing is that, okay, what is new thing in here? This one. Suppose you consider this thing. For example, if you consider n 1 greater than n 2 following this equation, if n 1 greater than n 2, then theta I should be less than theta t. So, theta I should be less than theta t. We forcefully consider this n 1 is greater than n 2. So, in that case theta I, this should be theta I must be greater than theta t, that should be theta t. So, that means in this case particularly coincidentally the sketch is actually the for specific condition n 1 greater than n 2, that is why it is, you see theta I and theta t, theta I is basically less than theta t. So, for this case it is suitable for this condition n 1 greater than n 2. Fine. So, after that, okay. So, next thing is that here, what is this? Now, if we use, of course, here you write typo error here theta I and this should be theta t. Now, if you see this equation, let us concentrate this equation. Okay. So, here you have theta I, theta t, theta t, theta I, both the equation involve theta I and theta t. But normally any interface what is happening, normally it depends on how we are signing our electromagnetic wave, it can be plane wave. So, theta I is known to us, but theta I to theta t, that is actually related by Snail's law. So, I can actually find theta t by using this equation. Okay. So, the sin theta t can be expressed as sin theta t equal to n1 by n2 sin theta I. So, if I know sin theta I if I know, then I can find out theta t. So, this cos theta t, if I can replace by theta I using Snail's law, I know that we know that this trigonometric relationship we can use, cos square theta equal to 1 minus sin square theta, right. Then cos theta t equal to square root of sin square theta t. Sin square theta t means n1 by n2 square sin square theta I. So, n1 by n2 whole square sin square theta I. So, now theta t I am representing in terms of theta I n1 and n2. So, theta t depends on not only theta I, depends on the refractive index of media 1 and 2. So, this cos theta t value I can insert here, this value I can insert here, this value I can insert here, this value I can insert here. Okay. So, all this value we can insert, then I can get our reflection coefficient in terms of only theta I and n1 n2, only theta I and n1 n2. That is straightforward, just we have used the Snail's law, because Snail's law is proved from the boundary condition, we can take it granted. Okay. Good. Next thing let us concentrate this one. So, after inserting cos theta t, this is the value of cos theta t, value of cos theta t, whatever the things we have put here, we have just written down there. Okay. So, then obviously you just keep on doing this theta I, theta t. I am sorry for that, this typo is continuing. So, copy paste. So, now let us move. What is that? Special condition we are considering, this one. When suppose you want to get a theta t equal to 90 degree, and that follows this equation. So, theta is always less than theta t. So, you can find a theta I value where theta t can be 90 degree. When theta I can be less than 90 degree, but theta t can reach to 90 degree, because theta is always less than theta t, because n1 is greater than n2. So, if I find theta t equal to 90 degree, that time whatever the value of theta I get from the equation Snail's law, that I will call as a theta c. Okay, that must be less than 90 degree. So, that is called critical angle. So, this will be I am putting n1 sin theta c equal to n2 sin 90 degree. So, sin 90 degree, this one is 1. So, I can find sin theta c equal to n2 by n1, sin theta c equal to n2 by n1. That means, theta c equal to sin inverse n2 by n1. So, critical angle is the angle of incidence corresponding to refracted angle 90 degree according to the Snail's law. So, according to the Snail's law, if you consider to have your refracted angle theta t is exactly 90 degree, that means your wave must graze through the interface in this direction, refracted wave. So, that particular situation to happen, you should have theta c angle, incident angle theta I equal to theta c equal to sin inverse n2 by n1. So, for that situation to happen, we have two things. If theta I equal to theta c, if theta I equal to, you are putting theta c, that means sin square theta c equal to theta c equal to n2 by n1. So, when theta I equal to theta c, sin square theta c equal to n2 by n1. So, that means this value will become 1. So, 1 minus 1 0, that means second term is completely 0, for it is happening 0, this is also going to be 0, and this is also going to be 0, this is also going to be 0. So, in that case this cos theta t, this value, particularly this value is 0, I have written. So, if that is the case, then your first term numerator, first term denominator is left over. So, if you just compare this one n1 cos theta I by n1 cos theta I, so gamma t equal to 1. So, gamma t equal to 1, we will be getting 1. Similarly, for gamma Tm, it will be minus, because this minus sign depends on, because you are considering magnetic field in the, here you are considering electric field and magnetic field. When they are changing after reflection, one of the field has to be reversed in the boundary. They will be oscillating with omega t, but at the boundary, when you are considering using boundary condition, at that particular instant upon reflection what happens. So, that is why minus sign, that is why I put a mode of gamma Tm, that is also 1. So, I can find a critical angle when electromagnetic wave propagates from the denser medium having refractive index n1 to rarer medium. I can find a angle theta c defined by sin inverse n2 by n1. I can have reflection coefficient 1. That means everything will be reflected back. Whatever is going, everything will be reflected back. Okay. So, if everything reflected back, what will be transmitted then? 0. So, one interesting thing is that if this is kt, I am just considering, okay, kt 90 degree we have considered, but when theta c is completely theta c is actually satisfying. So, this theta t has to be 90 degree. That means your ktx will be 0. That means in this direction, x direction, your component must be equal to 0. Obviously, if it is kt, then this ktx will be normally cos theta t, right, kt cos theta t. But cos theta t, as you can see, cos theta t is equal to this one, and if you are putting theta equal to theta c, that will be equal to 0. So, ktx is equal to 0. That means you can't see any wave propagating along x direction. Somehow it will not give, a ktx component is not there. So, no energy will be flowing along x direction. So, everything is reflecting back. That is called total internal reflection, total internal reflection. So, everything is coming to the first medium itself, nothing is in the second medium in principle as of now. Okay. So, I have written total internal reflection, sometimes it is called TIR, total internal reflection. Good. Obviously, this typo error is just correct, theta I, theta t. Sometimes you can consider theta 1 and theta 2 second media, that is medium 1, medium 2 you can consider also, that will work. Now, let us concentrate little bit differently. You just consider this one, concentrate on this one. So, theta I can increase and I can reach to theta c, and theta c I know that theta t will be 90 degree. Now, suppose theta I somewhere greater than theta c, greater than theta c. So, if greater than theta c, but theta I maximum limit will be 90 degree, less than 90 degree. Theta I somewhere greater than theta c and 90 less than 90 degree. So, in that case what will happen? So, if you see this value, if you are just considering n1 square, this value I am just concentrating on this one, n1 by n2 square to theta c, then it is n2 by n1, that will be 1 exactly at theta I by theta I equal to, whenever I am putting theta c, that time it is becoming 0, and below theta c that will be actually lower, less than 1. So, cos theta t value will be there, that is why you would see some transmitted wave is there, but exactly at theta c cos theta t has to be 0, that is why ktx will be, normally earlier we have discussed, that will be 0, but when theta c greater than theta I greater than theta c, this value will become more than 1. So, that means this cos theta t will become imaginary, this one will become imaginary, this is 1 minus 1, that is if cos theta t is becoming imaginary, ktx will be imaginary, because I know that ktx equal to kt cos theta t, okay, kt cos theta t. So, if cos theta t is becoming imaginary when theta I greater than theta c, then ktx is imaginary, right. So, I can have ktz will be there also and ktx also will be there, but ktx is imaginary. That means in the x direction you can see some wave field will be there, but since the propagation vector component that direction is imaginary, that means that direction it will be attenuated. As if you know the propagation constant gamma equal to alpha plus j beta, if something imaginary is there, that means it will be attenuating. So, field will be there, but it will be attenuating in the x direction. So, attenuating it will be very quickly, it will be becoming 0. So, that energy will not be flowing along x direction also. Okay. So, if that is the case, let us concentrate on this one also. So, this one will be also higher than 1 when theta I greater than theta c. If theta I greater than theta c, so this one will be higher than 1. So, this will be also becoming imaginary, and this one also will become imaginary. So, as a whole I see that this reflection coefficient gamma t and gamma tm is suddenly becoming complex. So, reflection coefficient is complex. Reflection coefficient is nothing but, so I can say that ER by EI, EI0, ER0. That means reflected wave, and this one is gamma t. When this is becoming complex, that means upon reflection, okay, upon reflection you see, if this is complex, upon reflection you can see that it is not only reflecting completely, but it may add some kind of phase. I am not sure yet whether it is completely reflecting or not. At least we see that reflection coefficient is complex. Reflection coefficient is complex. KTX is imaginary. So, at least it is indication that along x direction energy will not flow, it will be attenuating. It is like a skin depth in the metal, it will be attenuating. So, what happens to gamma t? How to calculate gamma t? If I just little bit work on it, you see cos theta t I can write like this, because this one greater than 1 I have just taken j outside, j equal to say square root of minus 1. Okay. So, if this is j, ktx imaginary, I can just write this one for theta I greater than theta c, that means in complex form I can write. Okay. How to write? I can write this one this way for this. Okay. When theta I sin square theta I is greater than this one, that means theta I, obviously when this is happening, that is theta I must be greater than theta c. This is theta I theta t. Okay. So, I have something like that. You have something A and you can consider J B. That means this one you will be getting like A minus JB by A plus JB. Okay. So, numerator and denominator is just complex value and complex conjugate, and if complex conjugate value, if you see in phasor form, I can write A square plus B square e to the power minus j tan inverse B by A, some angle will be there, and denominator also same value with an angle, plus and minus angle. Numerator will be minus angle and same angle, denominator phasor form it will be plus angle. So, that means, and absolute value also numerator and denominator they are same. So, that means I will be getting something interesting. If I just a little bit modify this one, then I will be getting very nice thing, this one. Let us concentrate this one, this highlighted one. So, gamma t will be just one value and then little bit of phase, because numerator denominator the same, complex conjugate just simply complex conjugate, their absolute value will be same, only there will be some phase angle. So, that phase angle I am considering phi t, and if you just take, this is the reflection coefficient for the amplitude reflection coefficient, but if it is reflectivity, if you just square it, then basically you have to take complex conjugate and multiply, then it will be 1. Okay. So, similarly this is also complex and this is a complex conjugate. Okay. So, this is your imaginary part and this is your real part, this is your imaginary part, this is your real part, and plus minus sign is there. So, there also you will be getting reflectivity, reflection coefficient 1, and certain phase will be there, upon reflection some phase will be there. So, whenever theta I greater than theta c, theta I greater than theta c, then you have total reflection, internal reflection, but you have also additionally some phase part is there. So, how to find the phase? That you can straightforward, just tan inverse B by A, tan inverse B by A, that will be the phase angle in the numerator, and tan inverse B by A also phase angle in the denominator. So, that is why total phase change will be minus 2 tan inverse B by A. B I am considering this one imaginary part and A will be this one. So, that is straightforward phasor form, you can just find out. Okay. So, I can see that when theta is greater than theta c, there also I am getting everything reflected, and you have KTX also imaginary, and reflected wave, this one is having certain kind of phase. What is that phase? If I just use this equation or this equation, I can find out what is phi t and what is phi t m. Simply you can just write down phi t e equal to 2 tan inverse this one. Okay. If you are writing minus sign here, gamma t e equal to 1 into e to the power minus j phi t e. So, minus sign we have included here. So, here phi t will be just plus 2 tan inverse b by a. So, in phi t m also you will be getting tan inverse b by a. So, the difference is that phase you see everything is same, 2 tan inverse, 2 tan inverse, here n 2 by n 1 and here n 1 by n 2, otherwise same. So, for T polarization and T m polarization, you will see that there will be certain kind of phase difference upon deflection, total internal reflection. So, this is how total internal reflection is possible. Condition for total internal reflection is theta I has to be greater than theta c, greater than equal to theta c. Theta c can be expressed sin inverse n 2 over n 1. Okay. So, for theta I greater than theta c, we know that this is actually n 1 by n 2 square sin square theta I, that is greater than or equal to 1, because exactly theta c this is 1. If theta I greater than theta c, then that will be greater than 1, and when that is greater than 1, cos theta t is becoming imaginary. Cos theta t is becoming imaginary means KTX is imaginary, because KTX again is KT cos theta t. So, that is imaginary. So, that means energy will not be flowing in this direction, it will be decaying along this direction. So, everything will be reflective. So, when it is decaying, that is why we have just decaying field we have shown here, that is called actually evanescent field. Okay. So, now we know that if you create a certain medium interface, medium 1 and medium 2, and if you adjust, if you know their certain refractive indexes, dielectric values, dielectric constant, then you can identify angle range which is greater than theta c and less than 90 degree, you can attain total internal reflection. When total internal reflection I am talking, it is penetrating, but in the penetrating in the second media like a metal in the second media, but in metal normally there is a sigma, it will cause some kind of loss because of resistivity, electron will move back and forth against a damping. So, some kind of heat loss will be there, scattering loss, absorption loss will be there, but since it is a dielectric medium, sigma equal to 0 in the second media. So, but the field is decaying, so energy will not be lost. So, everything will be reflected back ideally. Okay. So, if that is the case, then you can think of a lossless optical waveguide. You can use medium 3, medium 1 and medium 2. Medium 3 is dielectric also. You can actually characterize it by a refractive index n3, and medium 1 which is sandwiched between medium 2 and 3, n2 and n3 here, and this medium 2 is width is about just certain d. This is like a whatever you have considered like a earlier like a metal plate we were considering whether metal waveguide, optical waveguide can be realized or not, we discussed in the previous lecture. So, similarly you can consider same thickness, but surrounded by sandwiched by between two infinitely extended dielectric medium characterized by n2 and n3 refractive indices. Okay. So, in that case you can think of a certain wave is coming with an angle theta I, and if this theta I is greater than greater than theta cu, theta cl, that means critical angle at the lower interface. So, theta cl lower interface, in this interface, that should be sin inverse n2 by n1, and theta cu upper sin inverse n3 by n1, n3 by n1. So, if your theta I, somehow you set a theta I value, incident angle, that is greater than both theta cl and theta cu, then you can get total internal reflection here as well as in the upper interface also. So, anything theta I greater than this one and less than 90 degree, for example, then you can say that electromagnetic plane wave comes, go back and forth, and everywhere it will see total internal reflection. Similarly, complementary other direction, if it comes with the same angle, for example, theta I here, so it enter here, it will go total internal reflection here also. So, within a certain angle from this side and this side, if it is entering, they can actually propagate and can go like a, it can carry energy along the z direction. That is the propagation direction of the waveguide. Okay. So, since everywhere you are having total internal reflection, total internal reflection, total internal reflection, so you can have some kind of decaying evanescent field, because KTX in this medium, it is n2, it is j 2 pi over lambda n2 this one, because KTX is equal to, we can simply write cos theta t, whatever cos theta t, imaginary cos theta t you are getting, that is what I have derived earlier also. Similarly, KTX in this medium, it will be this one, it is imaginary, completely imaginary. So, since imaginary along x direction, field will be decaying, after some time it will be 0, in this direction this will be 0. Okay. So, I can ensure that electric field, electromagnetic wave, it will be decaying in medium 2 and medium 3. But what is there inside? In the core region, which is actually x0 to xd, it is typically in the order of lambda, that thickness should be, if 1550 nanometer we have shown on earlier, if theta equal to 45 degree, typically if it is a glass, it should be about 750 nanometer, in the previous lecture we discussed. So, what happens in the middle? In the middle you have KTX, you have one, if you see here KTX will be there and KTZ, and here also KTX, KTZ. So, that means KTX will be, one is positive x direction, another is negative direction. So, this is your K1, this should be N1, this should be N1, I am sorry, this should not be N2, okay, because in this medium refractive index is N1. So, KTX will be plus minus 2 pi by lambda N1, and KTZ will be 2 pi by lambda N1 sin theta I. If this is theta I, so we can have KTX equal to this one, this is also theta I. So, this is KTX and this is KTZ. So, KTZ equal to this one actually K. So, not KTX, that is KI I should get here, whatever longitudinal thing. So, this is actually KIX and KI, and this is actually KIZ, yeah, incident angle KY, incident it is coming. So, you can say that this one. So, in that case, so simply clearly you can see that you have counter propagating KTX component, the wave component you can consider, which is actually going along the x direction for positive direction and negative direction. So, two types of wave vector. So, that means in the x direction you can have a standing wave because of the KTX component, and KTX will be 2 pi by lambda N1, that is actually obviously real, that is not imaginary. So, that wave will be there, but it is counter propagating, it will create some kind of standing wave, that is actually called mode. Depending on the theta I value, certain theta I will be allowed, I will be discussing that. And in the longitudinal direction you can have this KTZ, that means whatever KT you are considering, that KTZ or KTIZ or inside whatever value, that is actually 2 pi by lambda N1. I can simply write, if I am considering just K, T I do not need to write, I just confuse with the previous slide, that is a transmitted wave whatever happening here. Okay. So, here actually transmitted, that is why KT we are writing, but inside it is typically KI. So, in that case you get this one, that will be only positive sign. So, that means in the forward direction it will be propagating. Obviously, you can launch from this side and total internal reflection can happen. So, negative side also it will be propagating. So, in that case KTZ will be this one, and this one sometimes we call it as a beta. That means this K transverse component inside the core that actually contributes to field confinement along x direction, and this component of the wave vector that actually helps to carry energy along the waveguide direction. So, that is how you can actually really design a lossless dielectric planar waveguide. So, light confinement in 1D. With this I close today. I will follow up this one to understand the how this modes distribution, different type of modes, how many modes it can support for a given value of d and for a given value of lambda. Those things we will be discussing in the next lecture. Thank you very much.